Alright, so we're going to talk about binomial and geometric variables. So we're going to learn what a binomial or what a Bernoulli trial is. We're going to determine how to find a geometric probability. We are not going to do this one because we already kind of did this one in the last section. And we determine how to find a binomial probability. Bernoulli trial. The two different probabilities that we'll talk about today revolve around what we call a Bernoulli trial. In order for a probability to be a Bernoulli trial, it must have all three of these characteristics. It must have a probability. There can only be two possible outcomes, and all trials are independent of each other. Let's analyze it a little bit more. This one's pretty obvious. It has to have some kind of probability, so it has to have a percentage of actually being able to do something. There can only be two possible outcomes. So essentially, you can either do that thing or you don't do that thing. There's no other possibilities. Which kind of locks into an either-or situation, a probability or not probability situation. And all trials are independent of each other. So basically that means that one thing does not influence the other, or every time they go up to do something, the probability will not change. That's basically what the independence of each other means. Let's take a look at it real fast. Now, for all my Ravens fans out there, I know this is not his actual percentage. I just made it up. Get over it. Take Justin Tucker, expert kicker of the Ravens. His overall kicking rate is 88.7%. If I wanted to do some probabilities on Justin Tucker, would this be considered a Bernoulli trial? Yes, it would, because he has a probability of completion. This is 88.7%. He meets the first criterion. He only has two outcomes. He can either make the kick or he doesn't make the kick, so there's no other possibilities. And every time he kicks, there's no influence on the previous kick and the current kick. You can make the argument that you can have kind of a factor of getting into someone's head, having some confidence issues, but that's not relevant, nor is it for every single kick. So that doesn't discount anything. So that makes them all independent to be the same. He had the same probability of kicking it in every single time. So this is a Bernoulli trial. Shaquille O'Neal was one of the better basketball players, but his free throw rate could be described as terrible at best. His overall average of all time was 52.7%. And I actually looked that one up, so that one's true. If you don't believe it, come at me. That's whatever. It's true. You can look it up. Use information to determine the following. First question is it a Bernoulli trial? So, let's look at that real fast. Is it a Bernoulli trial? So, well, to be a Bernoulli trial, so we have A. Does it have a probability? It does. He has a probability of 52.7%. He can. So he has only two possibilities. He can either make the shot or not make the shot. There is no in between. And each time he makes the shot, it's the same probability. So nothing changes. So from one shot to the next, they're all independent. Nothing influences the next shot. Okay, so the question is, what is the probability that he will make his first free throw? Well, he has a probability of making any free throw of 52.7%. So the probability of making his first one would be, I'm just going to convert it into a decimal, 0.527. What is the probability that he will not make his first free throw until his third attempt? So what that means is when you're not going to make it into your first attempt, that is, he'll make the first time he will fail to make it, the second time he will fail to make it, and the third time he will succeed. So that last successful try is 0.527. But if I wanted to find where he fails, well, there's only two outcomes. There's only two possible outcomes. And that is he either passes or he gets it in or he doesn't get it in. So if he succeeds to get it in at 0.527, then he's going to fail by doing 1 minus 0.527. So that would be 0.473. So both other times it's going to be 0.473. And then I want to go ahead and do the quick multiplication. So that gives me 0.1179. And then it says, what is the probability that he will not make his first free throw attempt until his fifth attempt? Now, technically what I'll get here is 0.437 times 0.437 times 0.437 times 0.437 times 0.527. And that's perfectly logical. But what if I want to do like the 100th or 90th time? You don't want to have to do that over and over and over again. So there's kind of a way to condense this. And the way you would do that in this case would be 0.473 squared times 0.527. So in this case, because he's going to fail 4 times and then succeed the last time, it would be 0.473 to the 4th times 0.527. And the way we know this is the 4th, because you're giving him, he's going to fail into the last time, and you're saying that he's not going to make it to the 5th attempt, so that means he fails 4 times and succeeds on the 5th attempt. So that gives me 0.473 to the 4th times 0.527. Is 0.0264. And that would be my answer to that. Okay, so what we get from that is kind of the idea behind the geometric probability. Geometric probability is essentially this. You keep failing until you succeed. Basically, it always involves not doing something until the last possible attempt. And the probability formula for this is 1 minus p to the x minus 1 times p, or you can kind of do it exactly the same way that we just did it on the previous one. But that's what geometric is. You keep failing until you succeed. Let's take a look at another example. Megan is attempting to pass the Praxis 1 math test. This particular test has a 60.3% pass rate. Determine the following. What is the probability of Megan not passing until her second attempt? What is the probability of Megan not passing until her fifth attempt? And what is the probability of Megan not passing until her 8th attempt? So we look here. So the probability of her passing is 60.3. So right off the bat, I want to do 1 minus 0.60. 0.603, and that gives me, let's see, 793. So what is the probability of not passing until the second try? Well, that's 0.397 times 0.603. And that would give me 0.2394, or 23.94%, as many of my students see me doing all the time, switching it over. 2, what is the probability of waiting until the second attempt? Sorry, not the second attempt, the fifth attempt, rather. Well, then we do 0.397 to the fourth, because it's 5 minus 1, and then do 0.603. And that gives me 0.014. Well, actually, it's 497, so we'll just put that out to 0.0150, or 1.5%. And then how about the 8th time? So now we're going to go to the 7th. So 0.397 to the 7th times 0.603, which gives me 0.0009. We'll do one more decimal place, 4, or 0.094%. Okay, make sure that's all on there. Okay, so let's take a step forward. So let's talk about binomial for a second. Oh wait, before we do that, here's the expected value of standard deviation for a geometric probability. Really not going to go into this too much, because at least for my class I don't really need it as much. I will need the next one, so we'll go into that a little bit more. But you can take a look at how you would find it. It's all right there. Alright, so binomial. Let's say you are about to take a 20-question test, and you determine that there is about a 83% chance of any question you answer being right. Determine the probability of getting 16 out of 20 questions correct. Okay, so this would be an example of binomial because we're going out of 20. So the other one you kept failing until you succeeded, and technically was infinite because you would have to, the end point was never static. You could go 3, 5, 7, whatever you wanted to go for. This one's locked into its 20 questions, therefore you can never go more than 20. So it becomes finite. Now, in order to figure out what this is, you first have to figure out how many different ways can you get 16 questions correct out of 20. Now, what I mean by that is this. You can theoretically get all the first 16 questions correct. 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and get the last 4 wrong. But that's not the only way that you can get 16 out of 20 correct. So the question is how many possible ways can you get 16 out of 20 correct? And now you don't want to go and try to calculate that by doing every single possibility. You will never get to it. So what you want to do is use this thing called the binomial formula. And did I use R in this one? I did use R. Okay, so what this is, and this is not a division problem, it's just n choose R. So basically we're going to do 20, so out of 20, we're choosing to get 16 correct. Now what this correlates to is this formula here. And no, that's not n. A little bit of humor, exclamation point joke. Okay, so what we're going to get is what's called a factorial. So it's going to be 20 factorial, 16 factorial, 20 minus 16 factorial, which translates into 20 factorial, 16 factorial, 4 factorial. Okay, so now what you're going to do is this. A factorial is basically something that gives you a starting point and then tells you have to multiply all the way down to, from that point all the way to 1. So for instance, 5 factorial, I'll put that over here. It'll be 5 times 4 times 3 times 2 times 1. So in this case, 20 factorial would be 20 times 19 times 18 times 17 all the way down to 1. Now, no one really wants to go do all that work, so we can do 20 times 19 times 18 times 17 times 16 factorial. And I'm going to leave it there, because what I'm going to do is I'm going to cancel out 16 factorial down here, and then say times 4 times 3 times 2 times 1. So these two are going to cancel out with each other, and it's going to make my life a lot easier. Because then all I'm going to do is say, okay, what's 20 times 19 times 18 times 17? And that gives me 116,280. And then on the bottom, what's 4 times 3 times 2 times 1, which I can kind of do in my head. That's 24. And then I'm going to divide by 24. And I'm going to get 4,845. Which means that if you have 4,845, that's how many ways you can get 16 questions correct out of 20. Okay, now to complete the binomial process, it works a lot like this. I have two possibilities. Either I'm going to get it right or I'm going to get it wrong. From a previous paper, I know that the probability of right is 0.83. The probability of wrong is 0.17. So if I look at that, what I get is 0.83, and I'm going to get 16 questions correct, so I'm going to take it to the 16th power. And then I'm going to have 0.17 for wrong, and if I get 16 questions correct, I'm going to get 4 questions wrong because it's a 20-question test, 16 and 4. And so that tells me the probability of just one of my options. But once again, I can do this 4,845 different ways. So I'm going to multiply my result by this. And I get 4,800, well, let's not do that first. Let's do 0.83 to the 16th power first. And then, I'm just calculating on my calculator right now. You might want to do that too. That gives me 0.2053 or 20.53%. Okay, and that's the same thing that would be on my next page. And kind of the exact same explanation. So we end up with 20.53%. So there's a 20.53% chance of getting 16 questions correct out of a 20-question test. Let's look at a couple more examples like this. So binomial example number 1. 15 people are applying for a job at Sears. Each has a 74% chance of getting a job. What is the probability that any 10 of them will get the job? Okay. So if we want 15 out of 20. No, wait, we want 10 out of 15. And we have a 74% chance of getting it correct. Or sorry, getting the job rather. So 15, choose 10, gives me 15 factorial, 10 factorial, 15 minus 10 factorial. Which ends up being 15 factorial, 10 factorial, and then 5 factorial. Okay, so I'm going to end up with 15 times 14 times 13 times 12 times 11 times 10 factorial over 10 factorial times 5 times 4 times 3 times 2 times 1. Get rid of those. 15 times 14 times 13 times 12 times 11 is 360, 360. 5 times 4 times 3 times 2 is 120. And if you ever do this division here and get a decimal, you know you did something incorrect because it should always be a whole number. So it ends up with 3003. So what I'm going to get is 3003 times 0.83. This to the... I'm copying the last question. 3003, my probability of getting the job is 0.74 to the 10th power, because we want 10 people to get the job. And then 1 minus 0.73 would be 0.26 to the 5th power, because 5 people aren't going to get the job. So 0.74 to the 10th times 0.26 to the 5th times 3003, and that gives me 0.1759 or 17.59%. Okay. Okay. Next example. So example number 2. Duracell makes durable batteries. Every time a battery comes off the line, it has an 8% chance of being defective. Knowing this, what is the probability that 3 out of 50 batteries can be defective? Okay, so we want 3 out of 50. Okay, and then the probability of it being defective is 0.08. So we're going to look at 50, choose 3. And so we're going to have 50 factorial, 3 factorial, 50 minus 3 factorial. Okay, so I'm going to do 50 times 49 times 48 times 47 factorial, because I can cancel it out with this bigger one right here. 3 times 2 times 1 times 47 factorial. Okie doke. So let's see, 50 times 49 times 48. So 117,600 divided by 6 is 19,600. So 19,600 times 0.08, and we want 3 to be defective, so this would be a 3 here. And then the opposite probability would be 0.92. And so if there's 50 total, we want 47 to be effective. So 0.92 to the 47th power times 0.08 to the third times 19,600 gives me 0.1993 or 19.93. Okay, and then the expected value. So the expected value equals n times p, and the standard deviation equals the square root of n times p times 1 minus p. Now these will be very important for the next thing I'm about to discuss, but until then you can kind of look them over real fast. And note that if we do it with the example with Megan, we would take her number, which is 20, times 0.83, which turns out to be 16.6, meaning she would have expected between 16 and 17 questions. And then we would take, to get the standard deviation, we take the square root of 20 times 8.3 times 1 minus 8.3, and that gives me 1.6799. But we'll look at that a little bit more with the next thing.